Hello, class. Welcome back to Calculus 2. Um, well, things have really been moving fast since the last time we met. I think that was March the 4th, maybe. Um, Everything seems to have changed. But the fact that you're watching this video is a pretty good sign. Um, I think we're in really good shape in this class to finish the semester. I hope everyone there is well and doing okay. I'm fine, and I think our little corner of the universe here in Calculus 2 will be great for the rest of the semester. There's a lot of announcements, of course, that have been coming fast and furious. Um, I'm sure from all sides at you. But I want to just call your attention to the things that are important for this class. And these are things that I've been sending in email, so I hope you've been reading your emails. I assume you have if you're watching this video, right? So I've posted these just really brief instructions, right? Originally, and these are summarized here in this syllabus addendum. You can click on this, or you can also find this in Blackboard under the class syllabus link. Originally, of course, we were thinking that we would only be online from March 23rd to April 6th, but you know that has now changed, so we're going to be online for the rest of the semester. So this document is already a little bit outdated, but it does summarize, of course, just sort of the basic information of how the course is going to be structured for the rest of the semester, which is pretty much I'm going to be giving you the lectures online, right? You'll still be doing your homework in WebAssign. I'll be posting the lecture videos and the lecture notes just like before the break in Blackboard, right? So the links will be in Blackboard in the class notes and videos linked there on your Blackboard page. And then, of course, other announcements will be posted here in WebAssign, right? Okay, and of course your homework is going to continue in WebAssign just like before. So in some ways, as I mentioned, right, the structure of the class will be very much like it has been. One thing I want to caution you about, though, is be very careful to read your email, right? I think you should be reading your email in general from the university. I hope you are. I'm sure you are. But be sure you're reading your email carefully from me, because that's really going to be my primary way of trying to contact you, right? Of course, I'll be posting announcements in WebAssign. I'll be posting announcements in Blackboard as well. Those are probably going to be duplicate announcements, but I'll be posting the same announcements in both places. And then when I post those announcements, I'll be sending them via email. So either be reading your email or be looking at, carefully at the announcements here on the right-hand side of WebAssign or the announcements in Blackboard, right? Because that's really the only way that I have to tell things to the entire class. Now, since I won't be able to see you face-to-face, I do need, of course, some way for you to talk to me personally. And so we're going to do that through virtual office hours, right? So I will be in Zoom virtually, right? Of course, that Zoom is that video conferencing software. I know you've heard a lot of it over the past couple of weeks because it's really been in the news a lot. A lot of people are using that, right, to do distance work like this. Anyway, I've posted this announcement in WebAssign and also in Blackboard about the virtual office hours. So if you want to ask me questions or just talk to me about other things, right, you can do that through Zoom, and the instructions here are given, right? You just need to download the Zoom app on your computer or on your phone. It works great on the phone as well. And then these are the designated times. I have Monday, Wednesday times, and Tuesday, Thursday times, and a Friday time as well, right? Where you can log into Zoom and find me, right? And we can talk face to face, or you can ask questions. You do need in Zoom a meeting ID, and so to join a particular session. So here are the meeting IDs. for the different office hours for the different days. I should have used just a single meeting ID, but I kind of flubbed that up when I was setting up these meetings. So they're different meeting IDs for the different days and office hours, but you can find those again in your website announcements or in your Blackboard announcements. Those will be permanent for the rest of the semester. Now, one of the lucky things we have for this class is that we have Taylor still available to us. So Taylor is also going to be available via Zoom. She's going to hold now her SI sessions, her tutoring sessions, during what used to be our class time, right, which is 1 to 2 p.m. on Mondays and Wednesdays. And so Taylor has already sent you a separate email about how to join her also via Zoom and what the meeting ID is for Taylor, okay? So you can still go to Taylor and ask questions, right, about the class. I did want to point out that the computer labs on campus, at least as of now, are still open. And so if you don't really have good access to a computer off of campus, you can come on campus to either the academic computing lab, which is on the 8th floor south, or to the library computers, down on the 4th floor north. These are all in the one main building, right? Or you can also go to the academic support center computers. The tutors will not be available live there in the academic support center, but you can do tutoring also via Zoom, and so be watching tutors from the academic support center. You can also contact via Zoom, so also be watching for instructions for that. So I know you got a lot of instructions coming at you for all of your courses, and so it's a lot to process here, but again, all of this is posted, so you can refer to it as you need it, right? I think this is this is both in WebAssign and will also be on the Blackboard page. Now, look, you can also, of course, contact me outside of Zoom as well. So you can email me, right, at my normal email address, or you can call me in my office. I should be in my office unless we get orders that we cannot come on campus. I should be in the office. If that changes, I'll try to find another number for you where you can call me directly and speak to me, right? So you've got plenty of opportunities to get in touch with me if you are having to ask questions, but in particular, if you are having some sort of hardship, right, that is going to make it difficult for you to complete the course, please contact me directly so I can either direct you to the resources that UHD provides that might be able to help you, or we can talk about what your options are maybe for dropping the class, right? But please let me know this, right, so I can provide what assistance that I can if you're having some sort of hardship. Okay, so I think I said most of the things that I meant to say, but let me repeat that the circumstances are not ideal, right? Since we're not able to meet face to face, and I really regret that because I like meeting with you guys in class. But nevertheless, we're in a really good position to conduct the class online because most of the stuff we do is online, and so we'll be able to get through this together, I think, pretty smoothly. All right. So I think. Provided that you've got, of course, the time and the resources, right, to devote to the class, and that might be difficult, right, under these circumstances. But if you do, then we'll be able to finish the semester almost like a normal semester. Now, another thing I did not mention is testing, right? So we're going to have to be doing testing remotely as well. So we're going to have to do that online. I have not completely decided yet how we're going to do the testing yet. So it may be just through WebAssign assignments, right, like your homework. We may do a test that way, or it may be written. So you may have to, I may post a test, you may have to write the test on paper and then email that back to me where I'll grade it. But as soon as I make up my mind about that, I'll let you know how that's going to work. Um, um, I think either way, though, will be fairly straightforward. And the first test that we'll have like this will not be until at least April 6th. So we've got plenty of time to talk about how the testing is going to work, right? Before we get to that particular point. In the meantime, of course, your homework assignments are still going to be in WebAssign, right? Okay, just like they've been before. All right, let's turn our attention now actually to those homework assignments because I have added one assignment here. This volume assignment that was, of course, posted before spring break, right? So, and we had finished the notes on volume. So that's not due until next week, however. Well, I'm sorry, that's due on Tuesday, March the 24th. So if you're watching this on Monday, that's going to be due tomorrow, right? So, so that will be due at midnight as usual. And then I have another assignment, and this is related to the things that we're going to talk about today in the lecture. And so that's Surfaces Revolution, which is very similar to volume, and that will not be due till March the 31st, okay, which is next week if you're watching this on Monday, March 23rd, okay. Now, I also didn't mention calculus flux. Of course, we're going to have to adjust, right, the nature of the calculus flux a little bit, but this system is still going to be in place. It's just how you earn the flux dollars will have to be a little bit different going forward. So as soon as I figure out how we're going to adjust that, I'll let you know. Okay, but flux dollars are your flux dollars I think are pretty much up to date, and so our system will still be intact, right, with the flux dollars. Okay, now, so normally here, of course, I'd ask questions, and sometimes I'll have questions, and sometimes you don't, but of course I cannot answer any questions now. So remember, right, you can find me, right, again, during my virtual office hours. The information is there posted in this announcement, and some of you have already found me in the virtual office hours, so so you know how this works. And, of course, you can find Taylor during her, also, virtually, right, in Zoom during her SI session. But if none of that's working for you, then again, email me or call me, right? Okay, and let me answer your question that way. Okay. All right, so I'm going to launch right into the notes now, right? We're going to talk about surfaces of revolution. This homework is really pretty short. It's only got 4 problems in it, so it's not a lengthy homework assignment. It does have some challenges related to it, though, and I'm going to bring those up when we're talking in the notes here, okay, about surfaces of revolution. Okay, all right, so let's switch to the notes here, and let's get started with this. So before the break, remember, we were computing volumes of solids, right? Let me show you a picture of such a thing, right? Let me scroll down here a little bit. So here's the first example we're going to do. I'll come back to this example in just a moment, but I want to use the pictures here. So remember, before the break, right, we had a curve. In this example, our curve is x cubed. There's the graph of x cubed. In this case, from x equals 0 to x equals 1 is the portion of the curve that we're interested in. So there's the graph of x cubed, right? Remember, we were going to rotate that around the x-axis, right? Okay, and then that when you did that, right, or actually we were going to look at the area beneath that curve and rotate that area around the x-axis, and when we did that, that swept out a volume, correct? Okay, so you got some sort of three-dimensional object there, or some three-dimensional figure, and it had a volume, and so we were learning, of course, before the break, how to compute the volumes of such objects, right? Now, in this section, we're going to do a very similar thing, except we're not going to be concerned with volume. Instead, we're going to think of taking the curve, but not the area beneath the curve, but just the curve itself, and rotating just the curve around the x-axis, or also we're going to do it around the y-axis as well. And when you rotate just the curve, but not the area beneath the curve around one of the two axes, what you're going to do is get a surface area, right? So you're going to get a hollow object. So it's not going to have a volume, but it will have a surface. And what we're trying to determine in this section is how to compute the area of such surfaces. That turns out to actually be, in a way, a little bit more challenging than computing the volume. You'll see here in just a moment what I mean. Okay, so in this particular picture, right, again, here we had the curve y equal x cubed. That's the blue curve here. It doesn't really graph very well. It's kind of broken there. But anyway, it's that curve, that blue curve, right? And then we're thinking of just taking that curve, not the area beneath the curve, but just the curve itself, and rotating it around the x-axis, and then forming a surface that way. So notice in this picture, you get kind of a trumpet-shaped object, right? And we want to compute what's the surface area of that trumpet, not the volume, but just the surface area. So if we were going to paint this trumpet, what would the surface area be that we would be painting? Now, we didn't do this for volume, but we are going to do it for surface area. Let me show you. We can also take this same curve. So this is what I'm tracing out here is still y equal x cubed, and instead of rotating that around the x-axis, we can also think of rotating that around the y-axis, and you get a little bit different shape in that case, right? But again, we're just rotating the curve around the y-axis, and so we're going to get just a surface area when we rotate that curve all the way around the y-axis. So when you rotate around the y-axis, notice you get same curve, but when you rotate it in that direction, you get a bowl-shaped object, right? And which you can see here. And what we want to do is, what we're going to try to do in this section is calculate what's the surface area of that object, right? In this case, of that bowl-shaped object. All right, so we're going to come back and actually do this example and actually compute these two surface areas in just a minute here. But let me show you now how this is actually done. Okay, so we're actually going to have a formula now. Of course, it's going to involve a definite integral, right, that we're going to use to compute these surface areas. I'm not going to derive this formula as carefully. Actually, there's two formulas. One when you rotate the curve around the x-axis, right, and then one when you rotate the curve around the y-axis. All right, so I'm not going to derive these formulas. Notice the formulas are kind of complicated here, so I'm not going to derive these formulas. I'm not going to show you where they came from exactly, but I will give you an idea of how these formulas come about. Okay, so here's the formula for computing the surface area formed by rotating a curve around the x-axis, right? So suppose you have a curve, y equals f of x, right, over some interval, right, along the x-axis. So for some domain there along the x-axis. And now suppose you take that curve and you rotate it, just like I showed before, right? You rotate this around, vertically around the x-axis. Then, of course, that's going to form a surface area. And here's the formula that you can use to find that surface area. Notice you get a really imposing here definite integral to evaluate. So S here represents the surface area, not a volume, but a surface area, right? And so it's going to be 2 pi times this definite integral. So the definite integral, the bounds on the definite integral are a to b. That's the interval, right, for the curve. And then notice now you take the absolute value of the formula for the curve. Notice you do have absolute value here. So it's absolute value of the formula for the curve, and then times this big square root, which is 1 plus the derivative of the formula squared under this radical. So as again I mentioned, right, sometimes these definite integrals, when you're trying to compute surface area, can be formidable to try to evaluate, right? Okay, but nevertheless, that's the formula. If you rotate the curve around the x-axis. Now, if you rotate the curve around the y-axis, you get a very similar formula, but slightly different, right? Okay, so in a way, it's a little bit simpler. So here the surface area starts the same way. You have 2 pi times this definite integral from a to b, and you still have this same square root in this integrand, right? Which is the square root of 1 plus the derivative of your curve squared, right? Derivative of the curve squared. But notice this factor in front of the square root is not the absolute value of f of x. It's just absolute value of x, right? Just absolute value of x. So maybe a little bit simpler integrand, right, than when you're rotating the curve around the x-axis. Okay, let me, before we actually do this example 1, right, let me show you just briefly the idea here of how this surface area formula comes about. Again, it's through definite integration, and you know what definite integration means, right? If we have some big quantity that we're trying to compute, right, what we can do is break that up into smaller pieces, right, and then add together the value of each of the pieces, right, the size of each of the pieces, and that would give us the size of the big quantity. And then, of course, in calculus, we like to think about what happens as we get infinitely many of those smaller pieces, right? We like to look at the limit as those tiny pieces get smaller and smaller, or we get more and more of those tiny pieces, and that limit, of course, is going to represent the size of the big quantity that we're trying to determine. So let me show you how we break a surface area into pieces. So imagine you take this curve. So I don't have actually the formula for this curve. This is just some arbitrary curve here, right? Y equals f of x. And it's from A to B, right, along the x-axis. And suppose we're going to take that, right, and we're going to rotate that around the x-axis, right? So again, that's going to form a surface, right? And we want to calculate the area of that surface. So, of course, what we want to do then is break that surface area up into little tiny pieces, right? Okay. And so in developing the surface area formula, what you're going to do is break that surface area up into these tiny little bands like this one that's sort of drawn here in gold here, right? These tiny bands. And notice these bands sort of look like pieces of cones, right? Okay. So if I took this one and kind of blew it up, right? Okay. You would get kind of a picture like this. This type of object that's kind of a piece of a cone, right? This is called a frustum. And we know from geometry actually how to calculate the surface area of a frustum, all right, like this. That's surface area of part of a cone. Actually, here's the formula from geometry, right, of computing the surface area of a frustum. So I'm not going to go through that formula because we're really not going to use that formula directly, but there it is, right? We do have a formula from geometry for computing the surface area of a piece of a cone like this one. So if you're trying to compute this surface area, this big surface area, right, what you do is you break it up into lots of little frustums, right, lots of little cones, lots of little sections of cones, right, and then you compute the surface area of each one of those frustums, right, using your surface area formula from geometry. And then just add those surface areas together of all those tiny little frustums, right? And that would give us an approximation for the big surface area that we're trying to calculate. All right. And then we just consider, of course, what happens as these frustums get thinner and thinner, right? As these little bands get thinner and thinner, or as we get infinitely many of these frustums, right? We just take the limit of the sum of the surface areas of all of those frustums, right, as the as the number of these frustums gets larger and larger, right, as it approaches infinity. And that limit, of course, will give us actually the area of the surface area of the big surface. So that's how the surface area formula comes about, right? We're going to take a surface and we're going to break it up into these tiny little frustums, right? And then compute the surface area of each of the frustums, and then add those back together, and then take the limit as the number of these frustums goes to infinity, right? In other words, as these frustums get thinner and thinner, right? And when we do that, we end up with exactly these definite integrals, right? That's where these formulas come from. Okay, all right. So now let's actually try. Now using these formulas, right? So let's look now at example 1. Okay, so here we're going to find the surface area of these two surfaces, right, that I already described just a moment ago. So let's start with the trumpet surface area, right? Let's imagine taking this curve y equal x cubed, right, from 0 to 1 on the x-axis, and we're going to rotate that around the x-axis and get this trumpet shape. And so we want to find its surface area. All right, so let's see if we can write down the definite integral right now that represents that surface area. So that's given in the notes, of course, earlier. Actually, let me just copy that here so we can refer to that. So let me copy this formula. And then we'll just fill in the, and then we'll just fill in the pieces, right, of the, let me erase this, and then we'll just fill in the pieces of the formula. Okay, so let's try filling this in, right? So we have 2 pi, right? And now our interval, right, is from 0 to 1, because we're only interested in this piece of the curve, right, from 0 to 1 along the x-axis. So my limits of integration here, a and b, are 0 and 1, right? And now we're going to take the absolute value of our function formula, right? The formula for that curve, which remember is x cubed. So absolute value of x cubed, and then the square root of, right, 1 plus, and now here's the part where we have to slow down a little bit, right? We need to fill into the brackets here the derivative of that curve, right? Well, remember the curve is x cubed, right? So its derivative is, that's pretty easy to calculate. It's going to be 3x squared, right? But don't forget now, this is actually squared. So I have here 2 pi, and then times there the integral from 0 to 1, right, of the absolute value of x cubed. Now I'm going to simplify this a little bit at this point because remember, x is only going from 0 to 1, right? So that means x cubed is never going to be negative because it's only going to be x is only going to be between 0 and 1 anyway. So I can drop the absolute values here. So that's nice, right? I can simplify by getting rid of those absolute values. And then here I have 1 plus, and now remember the derivative of x cubed was 3x squared, but I'm squaring that. So that's going to be, I think, 9x to the 4th power, right? 3x squared times 3x squared is 9x to the 4th power. All right, so now that looks a little bit better, but that's the definite integral, right, that we want to, see if we can evaluate. Okay, now, all right, so that's a pretty, looks like a pretty formidable, right, definite integral to evaluate, but I think we can actually do this by substitution. Um, Here's why. Because if you look under that square root, notice that the derivative of this quantity under the square root would be what? Well, the derivative of 1 is 0, and the derivative of 9x to the fourth power is 36x cubed. But outside of the square root, I have x cubed. So that's very promising, right? I think I'm going to be able to find an antiderivative, right, which I need to evaluate this definite integral. I think I can find the antiderivative of this integrand using substitution. So I'm going to substitute for the quantity under the square root. I'm going to substitute for that u. So let's let u be 1 plus 9x to the fourth power. And then du dx is going to be, as I mentioned just a moment ago, right, that's going to be 36x cubed. And what's important there is the fact that I have x cubed in this derivative, right, and I have x cubed there outside of the square root. I think that means the substitution is going to work good. Let's see. So when I solve this for dx, I think I get something like what? Dx is equal to du over 36x cubed, right? And now let's substitute here. So I get 2 pi. I really should change my limits of integration here, right? But I'm not going to. And then because we're going to switch back to x here in just a moment. I should change the limits of integration because we're going to substitute u for 1 plus 9x to the fourth power. So I'm going to change the variable here, which technically that changes the limits of integration. But since I'm going to eventually switch back to x anyway, let's not bother with changing the limits of integration. And then I get square root of u, right? And then dx, though, is du over 36x cubed. And just like I was hoping, right, the x cubes are going to divide out. Wow, what a relief there, right? So I have 2 pi, an integral from 0 to 1 here of, oh, well, actually, let me write it first. So I have 136. The 1 over 36 didn't go, right? And then didn't disappear yet. And then square root of u du. Now I'm going to factor the 1 over 36 out in front. So I have 2 pi over 36, and of course that's going to reduce integral from 0 to 1. And now let's see, the square root of u, I can write that as u to the 1/2 power, right? See, this is shaping up very nicely. Now I just have to find the antiderivative of u to the 1/2 power. But that I can find the antiderivative of using the anti-power rule, right? So all we have to do is just add 1, right, to the exponent, and then divide by the new exponent. So it's easy to integrate u to the 1/2 power. All right, so I'm actually going to carry out the integration. So the integral sign is going to be 1. So I'll have u to the 3/2, which is 1/2 plus 1, right, over 3/2. Now remember, we do have limits of integration though, so we're evaluating our antiderivative from 0 to 1. Let's see, 2 pi over 36, that reduces to pi over 18, right? Okay, and let's see, then I have u to the 3/2 power, but and now you're dividing by 3/2, which is the same as multiplying by 2/3. So let me write the divided by 3/2 as multiplying by 2/3. Now the 2/3 and the pi over 18, those two we can go ahead and multiply. So that's going to be 2 pi, well, let's see, pi goes into, 2 goes into 18 9 times, so that looks like this reduces to just pi over 27, right? Is that right? Yeah, 2 goes into 18 9 times, so you have 3 times 9 is 27, and then just pi in the top there. And now, u to the 3/2 power, well, remember, what was u? U was, I think, 1 plus, not, what was it? Let's see. What was u? 1 plus 9x to the 4th power, right? But that's raised to the 3/2 power. All right, so, and then we're evaluating that from 0 to 1. Okay, let's see if we can do that now. So I get pi over 27, and then now let's plug a 1 in for the for x. So when you plug 1 in for x, it looks like you're going to get what? 1 plus 9 times 1 to the 4th power, right? Raised to the 3/2 power. And then when you plug 0 in, you get 1 plus 9 times 0 to the 4th power. Don't forget that's raised to the 3/2 power, right? So there's a little bit of arithmetic here, but don't let it intimidate you here. So you have pi over 27. This looks like it's going to end up being 1 plus 9 times 1 to the 4th power is 10. So you have 10 to the 3/2 power, right? Minus, and then, of course, the 0 here to the 4th power is 0. So this just looks like 1 to the 3/2 power, which is 1. Oh, okay. So that's it. All right. You can maybe a little bit simplify 10 to the 3/2 power, but I'm not sure that's really necessary in this case. If you really are interested in knowing what this value is, you can use your calculator to simplify it. Oh, so there, I think that's our volume. Remember, that's going to be in square units, right? Because this, not a volume, this is a surface area, right? So that surface area is going to be in square units. I'm going to pause here for a moment, and then we're going to look at rotating this around the, rotating this also around the y-axis, okay? Okay, while we were paused there, I used the calculator to evaluate this area expression that we computed just a moment ago. So pi over 27 times 10 to the 3/2 power minus 1. And that is approximately, according to the calculator, about 3.56. So that tells us, again, that the surface area of this trumpet, right, that we get from rotating this curve y equal x cubed around the x-axis, the surface area of that trumpet is 3.56. Remember, that's square units, right? Square units, because we're computing a surface area, not a volume. All right, now we're going to look at kind of the opposite problem, right? We're going to take that same curve, y equal x cubed, and now we're going to rotate it around the y-axis. And remember, again, we have a surface area formula for that, right? And so here's that formula. It's very similar to, again, to the formula when you rotate about the x-axis, except this factor in the integrand in front of the square root is simpler. Instead of the absolute value of the function formula, f of x, you just have here the absolute value of x. All right, so so again, let's substitute here the correct values into this formula for this particular problem. Remember, our limits of integration were going to be 0 to 1, right? Because we were only interested in this curve y equal x cubed from 0 to 1 on the x-axis, and then times the absolute value of x, right? And then times the square root of 1 plus, and now remember, this is the derivative, right, of x cubed, because that's our function, right, squared. So we have the derivative of x cubed is 3x squared, right, and then we're and now we're squaring that. And so so we end up with 2 pi, again, times the definite integral from 0 to 1 of the absolute value of x. But again, since x is just ranging between 0 and 1, it's never going to be negative, so we can drop the absolute value here. So we just have x times the square root of, and then again, 3x squared squared is 9x to the 4th power, right? Unfortunately, this definite integral now is not easy to evaluate by hand, all right? So we do not have the techniques available to evaluate this one by hand. So if we want to evaluate this definite integral, we're going to have to get an approximation at using a calculator, or in this case, a computer. All right, so this is going to happen now frequently. Well, there are only 4 problems on the homework, but I think 3 out of the 4 problems will require you to use either a calculator or a computer to help you evaluate a definite integral, to get an approximate value for a definite integral. You're not going to be able to do this by hand. And so so you can do this with a calculator if you have a graphing calculator that can evaluate definite integrals, but you can do this with Decimus. So recall Decimus is this graphing software, right, that we've been using in the class. Let me see if I can show you how to use that, right? So there's a screen now that's already pre-built in Decimus called definite integral, and in this screen all you have to do is type in the integrand in this first line here where it says f of x equals, that's the integrand, and then just set your limits of integration, right? Our limits of integration in this problem are from 0 to 1, so I'm going to set the b value to 1 here. And then Decimus will give you the approximate value here of the definite integral to lots of decimal places. But you do have to type in the integrand, right? So so let's type in the integrand for our surface area rotated around the y-axis, right? That bowl-shaped surface area that we were looking at. So remember now, that's going to be x and then times the square root, right? So you can get, you know, there's a palette here in Decimus, right, where you can type in a square root, and then it's 1 plus, right? And then it was 9x to the 4th power. To get an exponent in Decimus, just use the caret key, which is the shift of the 6th key, right? And it will give you an exponent. Now, however, remember the formula also involves 2 pi, okay? So you can do that in a couple of ways. You can either go ahead and find the approximate value for the definite integral and then multiply it by 2 pi. So in this case, that is, notice that's about 0.942, right? And then you would multiply that by 2 pi to get your surface area. Or if you like, just go ahead and type the 2 pi into the integrand, okay? And then you don't have to worry about multiplying by 2 pi yourself. So I'm just go ahead and put the 2 pi in the integrand. Decimus is smart, it knows pi, so if you type in pi, which is the spelling for the Greek letter pi, it will automatically convert that to pi for you. So there is our there is that value of that definite integral, right, from 0 to 1 of our integrand. So it's about 0.5919, etc., right? Okay, so there, that's nice in a way because we don't have to do a lot of things by hand, right? We just type that definite integral right into Decimus, and it gives us the approximate value for that definite integral. Let me check that again to make sure we did that right. Yeah, 2 pi x square root of 1 plus 9x to the 4th power, right? And that's about 5.919. Notice Decimus is going to draw a picture of this definite integral, but that picture does not correspond to the surface area, right? Okay, so sort of don't pay attention to the to the graph here that's drawn over on the right-hand side. You're only interested in this computed value, 5.919. Okay, so there's approximate. Remember, this is square units, right? So there is approximately the surface area of this bowl up here, right? It's about 5.919 square units. Okay, so again now, in your homework problems, when you're computing these surface areas, you're going to have several problems, right, where you're not going to be able to calculate the definite integral by hand. We just don't have the integration techniques available to us yet to do that. So you're going to have to rely on something like a calculator or perhaps Decimus. Actually, let me look at the homework here quickly, if we can get the screen to switch back, and I'll show you the problems. So there's our surface of revolution homework, right? Let me open that. So hopefully this will open easily. And we'll take a look at a couple of these problems just to show you, right, what I'm talking about. So the first problem, I think that one, notice there's lots of things to fill in, right? How, they want you to fill in this this definite integral, right, that you can use to compute this surface area. This is very similar to the example that we just did, so that should be pretty easy to follow that example and calculate. Here you're rotating this curve 1/3 x cubed around the x-axis, right? Except you're going from looks like from 1 to 3 here instead of from just from 0 to 1. I'm sorry, from 0 to 3 instead of from 0 to 1. So I think this one you can do by hand, okay? However, notice it is asking you to round your answer to 2 decimal places, so pay attention to that. However, problems 2, I think problem 2, you're definitely going to have to do that with the help of Decimus. And problem 3, now you can probably do this one by hand. I think you can do this one by hand. This is rotating around the y-axis. But still they're asking you to answer to round your answer to 3 decimal places, and then the last one I think you'll have to do that one using definitely using a computer or a calculator. All right, so at the top of this homework now, notice there is the link right there on the second line. There's the link that you can use in Decimus to do definite integration. So if you click on that link, it will take you, I think, to something very similar to that screen that we were just looking at a moment ago, right? So let's see if Decimus will start here a second time. I've already got it running. There it is, right? Okay. So there's that screen for definite integration, right? So you just have to fill in the integrand there. Remember to include the 2 pi, right? Okay. That's part of the formula, and then fill out your limits of integration properly, right, and then you can get the decimal approximation for that definite integral. Okay, so so we're done with our first lecture, right? Our first video lecture for our new online Calculus 2 class, and the homework for surface area is posted. Remember, please visit Taylor using Zoom, right? During Taylor's SI sessions, which are going to be during the regular class time, and Taylor has sent you an email about this with the correct meeting ID. And visit me during my virtual office hours, also in Zoom. And again, those well, let's see. Let's go back here. Again, those meeting IDs, right, are those meeting IDs, right, are in the announcements, right? Right here are the meeting IDs you can use, right, in Zoom, right, to visit me, right, during my office hours, which are the same times as they were before the break, except I added this extra Friday 10 to 11 office hour, right? If you're having trouble using Zoom, just email me or call me, and and we can I can show you how to use this. It's really very easy. Okay, there's also lots of help on campus for using Zoom, because lots of other professors will be using Zoom to have office hours or to conduct class. So I think you're going to get you'll be a skilled user of Zoom before this is over with, if you're not already. And again, now remember, if you're having hardships, right, personal issues that are going to make it difficult for you to complete the class, please call me or email me, right, okay, so that I can respond to those, okay? All right, so you know your homework, right? It's posted in the usual place in WebAssign. Our next lecture will be posted for Wednesday, right? We're going to get back to, we've been looking at applications of integration with differential equations and volumes and surface areas, and now going to get back to learning some new integration techniques, some really important integration techniques, more powerful integration techniques, starting with a really important technique called integration by parts. That's really something that you want to have knowledge of before you leave this class, is integration by parts, because you will be using that in future classes for sure. All right, so that's going to be an important lecture and homework for Wednesday. All right, so I will talk to you again on Wednesday, right? Okay. Hope everyone is doing fine. Stay safe. All right. Wash your hands. Okay. And as always, we're going to get through this together. We're going to do great.